I wanted to thank you all for coming. My name is Amol Kapoor, and along with my coworkers, I've spent the last year or so working on Nostalgin at Google Research in New York City. So, what is Nostalgin? Nostalgin is short for the Nostalgia Engine, and it aims to be a platform for virtual collaborative time travel. Basically, we want to allow users to visit the past using advances in deep learning to recreate photorealistic virtual worlds from old images, photos, films, basically any historical data that we can get our hands on. Right now, historical data is uniquely hard to interact with in the modern world because it is fundamentally analog if it exists at all. This is in stark contrast to, say, Netflix or Google, where it's easy to access and there's a lot of it. The only place where most people can interact with historical data is in museums. In the same way that museums allow people to interact with history, we want to make it easy for anyone to experience the past. We say that Nostalgin is a collaborative time travel effort because we want the project to be open source. At the end of the day, we want users to work together to build a collective understanding of history by sharing their own images and maps and whatever else. All right, so that's it for the vague vision stuff. Let's make this a little bit more concrete. This image is a prototype example of the sort of thing we want Nostalgin to do. The image is a reconstruction of a city block that was built by Nostalgin. We fed Nostalgin historical images of 1940s New York City, and we got out a 3D world that we could walk around in, as if it was a video game. How do we get there? I'm going to spend some time today talking about the problems that we faced building Nostalgin, what our solutions were, and what we're doing moving forward. The overarching issue that we faced with Nostalgin was a lack of data. It turns out that historical data is super sparse, and we are generally lucky to get even a single image of a building. On top of that, almost all of our images have zero metadata. We generally don't have information like GPS coordinates, for example. It's a bit funny talking about sparse data at KDD. In the era of big data, where thousands of images can be found with a simple image search, it's easy to forget that data used to be a lot less abundant. Because historical data is so sparse, we were forced to frame this problem as a data generation task. Given some small amount of data, we need to extract and extrapolate. Such extrapolation is feasible only because we have some known priors about what the world is like, that we can encode using advances in deep learning. It's important to note that we need a lot of intermediate data in order to do a realistic generation. What does intermediate data mean? Well, let's think about a simplified example. If we're going from an image of a cube to a 3D model of a cube, it's not about just generating extra vertices. We can't just generate those vertices at random. The model needs to somehow infer key information, like height, width, and depth. We call this intermediate data, key pieces of information that are necessary to make an accurate final prediction. In short, we need to be smart about where those vertices are. We use intermediate data states to figure that out. Because historical data is sparse, we had trouble starting this project. And so to that end, I want to thank the New York City Municipal Archives, who provided us with a starter set of photos of New York City. It turns out that in the 1940s, the New York City government went around and took pictures of every single building in the city for tax records. Those images still exist, and they're an absolute treasure trove of information for us. And we're really grateful that the archives in charge of maintaining that data gave us some of it to play with. If this is the sort of thing that interests you, I really recommend checking it out. There was a New York Times article about it a few years ago, and you can still find that information online. All right, so what did we actually end up doing with that data? This is the structure of the Nostalgin pipeline, a series of discrete steps, each focused on generating specific intermediate data states to support the final result. The focus on intermediate data is actually really important. It turns out that deep models are not great at inferring vital intermediate data states. We're deep learning people. Our gut instinct was to try an end-to-end deep learning model that goes from 2D straight to 3D, and that was ridiculously difficult. We just could not get the thing to work. By explicitly generating important intermediate data, we could in turn use that data to infer more downstream data points. Our pipeline is composed of 5 steps: segmentation, matting, rectification, inpainting, and modeling. In this diagram, you can see how a single image goes through each stage and is modified and added to until the 3D model is generated. And since this came up yesterday, I want to point out that this is actually all the same image that's going through this pipeline. In this presentation, we're going to go through and describe each step, starting with the segmentation and the matting. Segmentation is a way of adding content metadata to raw pixels. It allows us to go from unstructured and unrelated pixels to discrete relationships between points. In the example here, we are specifically segmenting buildings. Another way to think about it: we cannot enforce known priors like buildings are generally cube-shaped or they have windows and doors until we know where in the image the building actually is. Matting is a way of sharpening the segmentation outputs. We use a process called alpha matting, which is a conventional image gradient approach that attempts to use the differences between 2 pixels in order to sharpen the edges. The idea of using these deep and conventional approaches in tandem arose naturally while trying to improve our system. We found that deep models alone were not sharp enough. In our experience, when it comes to pixel maps, machine learning just does not like sharp edges. Instead, it prefers these nice probability distributions. This is pretty easily visible in the second column. Because of the nature of extrapolating information, it ended up being really important that we don't accidentally propagate error. Small mistakes in upstream tasks led to absolute garbage in later stages. Using conventional approaches like matting to supplement the segmentation actually removed a significant amount of downstream error, as seen in the fourth column. The combination of deep and conventional methods is something of a theme of this work, and we'll come back to it later because at each stage we found that we could augment our deep outputs with conventional approaches. All right, so the previous step allowed us to identify objects in the scene. Now we want to build off of that information to generate some more metadata, in this case, object orientation. Understanding object orientation is really important for downstream tasks. For example, it's really hard to understand if windows are the same size or not when the building that they are on is tilted in the scene. It's only when you're looking straight on at the underlying building that you can see how things are actually sized. Let's talk about the process. We start with segmentation. The rectification stage builds directly on the previous intermediate content metadata. Once we get the mask, we find all of the edges in the image. We look for linearity to identify lines that would indicate where the building is pointing. And finally, we use those lines to determine the orientation of the building. In that last image, the green line represents the horizontal axis, and the red is the vertical axis. The blue is just a contour around the building. The green and red lines make up the orientation information for the building. Once we have those orientation lines, we know that they should be roughly perpendicular. That gives us enough information to do a matrix transform, which gives us a rectified output. Note that in the rectified output, all of the perspective is removed, and the windows end up being the same size. So at this point, we have a few more pieces of metadata. We started with raw pixels, and now we understand what is in the scene, and we understand how it is positioned. Now we want to explicitly modify the scene. Specifically, we want to remove objects in the scene that block the building, like that car. We call these objects occlusions. First, we use segmentation, again, to figure out where those occlusions are. Then, we use a deep model to make that car vanish. The inpainting step is explicitly about generating new dense image information where we didn't have it before, based on background information and background patterns. We do inpainting with a conditional GAN. The generator takes in a masked image and attempts to produce a inpaint. The discriminator examines the patches of the inpainted region and attempts to determine if that inpaint is realistic. As with segmentation, inpainting benefits from several conventional approaches. First, we explicitly run the inpainting after rectification, because running on rectified output makes the pattern recognition much easier. This is because things like windows are now the same size, so the inpainting model can recognize those patterns a lot more easily without having to waste parameters and computation on identifying the depth in the image. In other words, using segmentation and orientation data as intermediate steps allows us to generate new dense pixel information better. In addition to that, to speed up the computation, we intelligently split large masks to optimize the inpainting model output, and we post-process using gradient smoothing to make the inpainting boundaries seamless. Again, we see this pattern of deep models being improved by conventional methods both in pre- and post-processing. While the goal of our inpainting model was to remove occlusions, we found that the model learned about buildings and images generally. As such, we were able to use the inpainter to get rid of other kinds of noise. We can use segmentation on noisy sections and then get the inpainter to clean up the images. Just to highlight these changes, you can see exactly what kind of noise we were removing. The noise in the left images mostly come with age. For example, the residue is probably coming from some sort of sticker that was damaging the original image. So not only are we able to get rid of occlusions, we are also able to denoise our images. So we started with just raw pixels, and now coming into the modeling stage, we have a lot of useful extra information. We know where the buildings are in the scene, we know the pose of those buildings, and we removed anything in front of the building. We can use this data now to intelligently generate our models. Nostalgin is still a prototype, so there's still more to do. Currently, Nostalgin cannot predict inter-image relationships. We don't have a good way of determining how to place two buildings next to each other or how they're relatively scaled. We're working on extracting that data from historical maps, but right now, Nostalgin ingests that data directly. We also currently assume that the basic structure of our buildings is cuboid, which works for New York City, but probably won't work for the suburbs and other places. All right, so let's put it all together. Here's the end-to-end, the same image going through segmentation, matting, rectification, inpainting, and modeling. Each step builds on what came before. Working with the New York City Municipal Archives, we used Nostalgin to recreate a few blocks of Chelsea as it existed in the 1940s. Because we generate full models, we get novel view synthesis for free. Also, because we never parameterized or simplify the dense image information, actually we add to that dense information, we get pretty detailed outputs. We render all of this in a 3D environment that users could walk around in like a video game. I'm personally just really excited about the stories that you can tell with this sort of thing. I think the then and now comparisons are really, really cool. So on the left, you can see the original image from the 1940s. In the middle is a screenshot from the Nostalgin reconstruction, and on the right is the modern day. Because this building was torn down since the 1940s, there's no way for a user to experience that building anymore, even if they went to that exact spot. And I know this because that spot is actually 2 blocks away from where I work. The only way to do so, to walk around in that area and to step into that scene, is through a system like Nostalgin. Remember that that apartment was likely somebody's grandparents' home or somebody's family home. And as a result, we think that users can have a very emotional connection to this sort of experience. It's also worth noting that this building in particular is pretty interesting. Even though it was completely torn down since the 1940s, it's still a bank. All right, so that was what we had when we submitted this work to KDD. We've been working hard since then, and I want to use the rest of my time to talk a little bit about what we've been up to. The basic idea is that we want to remove our dependencies and improve our outcomes. On the left, we want to incorporate data that's been extracted from other sources, like historical maps. And on the right, we want to move away from our cuboid assumption and add realistic bump maps to make everything look more realistic. Historical maps data obviously contains a lot of information about geolocation, but it also contains important information about relative height and width, and it helps us figure out incidentals about the building, like sidewalks and locations of doors and windows. Currently, we're working on geo-rectification to line up historical maps data with current maps data. This allows us to utilize modern metadata and infrastructure without building locations. In other words, we can then tap into the modern infrastructure that exists and use that to supplement our historical data. When we do have metadata, we want to be able to smear that around. To that end, we embed these images using a deep model trained to optimize some sort of a similarity measure. We use these embeddings to create a graph, and then we place new images in the graph to determine where that metadata should be spread. In the example here, we are explicitly looking to see if we can find multiple buildings, the same building with multiple viewpoints, which in turn will give us more information and improve our depth outcomes. So that's a bit on what we're doing on the extracting metadata side. On the other side, let's talk about what we're doing to improve our modeling. Like I said, we want to move away from assuming that all buildings are cuboids. To that end, we've been working on primitive analysis and have begun identifying basic structures for other building classes using basic classifiers combined with voting algorithms. So while originally we could only figure out the depth predictions for cuboid buildings, we can now also figure out how to go from a triangular roof house to a primitive of the same. We've also been working on extracting depth from facades in order to get that extra wow factor. Right now, the buildings that we generate are flat, which is especially visible when you walk up to them. We're working on making awnings, signs, fire escapes, windows, etc. pop out for added realism. Extracting these depth maps from black and white pixels alone is actually pretty tough. And so we've been supplementing our training with modern data there. Luckily, we can tap into Google LiDAR data to train black and white to depth models. All right, so a few closing thoughts. Even though it's against the conventional wisdom, we found that in applied settings, end-to-end learning is really hard. Throughout building Nostalgin, we tried doing end-to-end learning where possible, and this proved really difficult. We just could not get our deep models to infer the intermediate data points that we actually cared about. It turns out that modularity matters even in deep learning pipelines. We were only able to make progress when we split our pipeline into many different pieces. It's possible that if we had more data or better data, we wouldn't have this issue, but this isn't an option when you're dealing with historical data. In sparse settings, we need to be much more aware and a lot more careful about how each data point is being used. So I know that this slide is probably something that you've heard before, but it ended up being so important for Nostalgin that I really feel like I have to stress it. As we built Nostalgin, we discovered that we had a serious problem with compounding error. Deep models don't give clean outputs, and deep models built on top of other deep models just don't work that well. All of our deep models ended up being improved by using conventional approaches to enforce known priors. It turns out that deep ML is pretty good at getting us about 80% of the way there, but the conventional approaches were crucial for the extra 20%. Finally, I want to emphasize that we really want Nostalgin to be a collaborative effort. This is the first time we're talking about it to the public, and we want this to be a stepping stone to get people involved and excited. So if any of this seemed cool to you, contact my teammate Sasan, or you can reach out to me or email me or whatever. And that's it. I wanted to give a shout out to these amazing people and a special thanks to the organizations that supported us in bootstrapping this effort. I also want to thank everyone who came to my talk yesterday at the UrbComp workshop and who dropped by the poster presentation. If you stick around or find me afterwards during the break, I do have the live demo of Nostalgin actually on my computer and would be happy to show people what it looks like. Actually, I mean, if we have additional time, I might be able to even do that now. It's kind of, what do you think, Mohawk?
Yeah, we're like 4 minutes.
I got 4 minutes? Okay, cool, great. Yeah, so let me actually switch over to that, and we can, let's see here. Does that work? Maybe? Yes, okay, cool. All right, so this is a reconstruction of 2 blocks of Chelsea as seen in the 1940s. I'm gonna put down the microphone a little bit so I can walk around. So you can see that it's actually a full 3D world. You can actually walk around in it as if it was a video game. It's WASD controls. You can move around. You know, you can like actually move your head around. All this, and I think this is just really cool because a lot of these buildings don't exist anymore. So for example, like we were showing before, this was kind of the original shot. This is the actual image that we used to reconstruct that shot. So you can see the similarities here. And this is what that image looks like today, right? So there's that same Valley National Bank. This whole building was torn down. It's now this glass structure. But you can actually see that this building over here is the same as it was in the 1940s. And I think this is especially cool when you go to a place that has like, you know, much more of the area torn down. So like this avenue that we're looking at right now, all of these buildings were torn down to make way for this school. So all of these were actually at one point apartments, which means that people lived there. You know, people actually have emotional connections to these places. And so the only way to actually experience what it was like going down this avenue as if it was the 1940s would be through something like this. We have a lot of really cool ideas of what we want to do with Nostalgin. One of the cooler ideas that I really like is, for example, we want to do a history of street art. Street art is something that is inherently transient. It gets washed away. The buildings, you know, get painted over, whatever. And so we think that if we can take photos like that and actually make them fully realizable virtual worlds, we would allow people to interact with them as if it was, you know, as if they were actually there. And this is really just kind of a prototype in that direction. It's also worth noting that some of these images are, you can really sense that they're flat, right? So if you go up to this building, for example, you immediately see that these are not actually, like they're not popping out. And so that's what we've been working on over the last 6 months. And the other thing is you'll notice that some of these images are much better than others. So like this building in particular had a really, really good corner shot that we were able to extract some good information from, whereas some of these buildings down here start getting really fuzzy and pretty blurry. And the reason for that is because we're dealing with sparse historical data, we just don't have that information available. So what we hope to do is create a system in which people can upload more information and we can use that to supplement the data where we know that something better should exist. And I think that's it, yeah. So again, if you want to come meet me afterwards, I'll show you this in more depth if you want to just kind of play around and walk around in it. And again, if any of this seemed interesting, please reach out to us. We would love to have collaboration. And yeah, so Q&A.